Okay, so now we're going to talk about cis-trans isomerism of cyclohexanes. When you have a disubstituted cyclohexane, you might have both you might have both groups above the ring, or one above the ring and one below the ring, right? This is called a cis because they're on the same side, cis, and this is called trans, right? So we're using Hayworth projections here, which I told you a little bit ago we're not going to use much. But Hayworth projections are nice because it's really obvious that they're both up, or one's up and one's down. Okay, so these are called stereoisomers, and we're going to get into stereoisomers more next chapter. But stereoisomers have the same atoms connected, the same bondedness, but they have different physical properties. And you can imagine that if there's some kind of a steric interaction here, like repulsion between those two, that can be relieved by these guys, right? By one going on one side of the ring and one going on the other. But you could say, wait a second, I have a methyl group on the one carbon and a methyl group on the two carbon, a methyl group on the one carbon and a methyl group on the two carbon. But these two methyl groups cannot get as far away from each other as these two can, right? So this is called cis because they're on the same side. This is called trans because they're on the opposite side. And again, they're stereoisomers. All right. So we're going to need to also appreciate that they both exist in chairs, right? So what you have here is an axial position. I'll put squares around the axials, axial position, axial position, and axial position, and we'll do circles for the equatorial, right? Equatorial and equatorial, and then equatorial and equatorial. Now, can you imagine that if it costs energy to go into the axial position, that this is going to have some cost? Looks like that's going to have the same cost, right? I've got one in axial and one in equatorial, right? But here I've got two in axial and then 0 in the axial position. So it turns out this is going to be the highest energy because it's got 2 in the axial position, and this will be the lowest because it's got 0 in the axial position. And these two are equal in energy because they each have only 1 in the axial position. All right, so it's going to be, I'm going to put this into, like, look, hash wedges, right? It turns out that, let me do a different color for the hashes. Can you see these wedges and hashes? Okay. So it turns out that if this is axial, then this will also be axial, right? Why is that? And this will be axial. Why is that? And this will be axial. You know, I'm not going to tell you. I'd like you to draw these. You should draw these out. We said before, like a wide V, right? 60 degrees. That wasn't quite 60. Parallel with that one. Nope, not parallel with that one. This needs to be parallel with that one, right? And then this one's parallel with that one, and then boom, right? So there's our chair, axial. I said I wasn't going to tell you, but I just did, didn't I? You should draw this out. You draw it out, all right? And prove to yourself that axials are 1, 3, 5, and going up, 2, 4, 6 going down. Yeah, prove that to yourself. And then also, we'll have a chance to practice more of what it means to have disubstituted cyclohexane rings, and we'll be naming them cis and trans.